right, let's get started. Good morning. Welcome to the session on reactive programming in Java. My name is Venkat Subramaniam. We're going to talk about reactive programming in general, and then we'll talk about some examples, how it works. So let's get started. I want to first talk about reactive programming itself. So the first question I will start off with is the question, why yet another programming model? Why can't we just be happy with what we already do? Well, one thing I've realized is we work in a field where about every 10 years we'll give a new name for what we already do and really get excited about it. So this time around, things that get us excited are things like reactive programming, microservices, and things like that. Well, it turns out reactive programming is really not new. It's been around for a very long time. In a way, if you really think about it, it's kind of like what extreme programming did. Well, extreme programming didn't have anything new, and what was really new about extreme programming was it brought together certain practices we should really focus on. In a similar way, the things that reactive programming brings together has been around for a while, but what reactive programming really does is brings the emphasis for really why we should focus on those 4 specific things it talks about. So it's really a rehashed programming model that emphasizes on scalability and responsiveness. But the question is, why should we really care about it, and why now? Well, I'm almost nostalgic when I say this, but I remember the days when I would wake up in the morning while the coffee pot is brewing coffee, my modem will connect and reconnect, and I can hear that whoosh noise in my ears. And then, of course, I would call my friends and ask them what baud rate they're getting today. Well, those days are long gone. Now we are dealing with devices that are constantly connected to the internet, always connected. Every one of us carries around multiple different devices with us every single day. And as a result, we have applications that constantly are working with data, passing data around. Well, the second significant thing that's happened is, if you really look back about 10 or 15 years ago, companies made software available to their employees and made their employees available to the internet public. Well, those employees who are using the systems are called captive users. It doesn't matter what they think about. On the other hand, we have applications being available to real-world users now. Well, it doesn't matter what the size of your company is. I bet you have more customers and users than number of employees. So as a result, we have a lot greater demand on applications now than once we did years ago. And then, of course, we are also talking about various different devices constantly communicating. Well, forget about smartphones and watches. We're talking about earrings and nose rings and tongue rings, all internet-enabled very soon. What that really means is we are looking at devices that are connected to us, maybe constantly monitoring our health status. Imagine your doctors can be notified about your health status even before you realize, and they can come down to help. Those days are not very far away. So we are talking about applications that are constantly exchanging data. We're also talking about high volume, high frequency, what we call as big data. That's where we live today as well in a lot of different applications. So it's a way to really structure and scale applications. This particular idea came from Microsoft Research. Eric Meyer created this idea of reactive programming, and it's been around for quite a number of years before it gained popularity in the field of Java and JavaScript. It's been around in the .NET area for a fairly long time. But the main idea is the word reactive in this case simply refers to the ability of a system to respond to stimuli and activities as they happen. So when it comes to these applications, I want you to step back and rethink about this just a little bit. If you look back at the past 20 years, what have we been doing for a good portion of that time? Well, we can pretty much summarize that into one acronym, which is CRUD. So most of the applications we've been building is CRUD applications. We create data, we read data, we update data, and sometimes we delete data. But at some point, you wake up one morning and ask the question, is everything a CRUD application? Is it possible that maybe you've just gone overboard? Maybe you're just thinking about everything as CRUD. Maybe not everything falls into this category. Well, it turns out that is actually true, that there is a lot of applications that don't quite read data, process and set the data back like the way we think about it. There is a wealthy of applications that are interested in processing data that might be flowing through as time goes on, and we want to be able to respond to these activities. These are intermediaries. Imagine you are interested in processing stock data as the stock data comes through throughout the day the stock market is changing, you're not reading the stock data from a database per se. All you're doing is you are responding to the stock data. Hey, I want to purchase the stock price at this particular time, but I want to wait until this price really comes to that particular point, and when it does, I want to really act on it. I don't care about anything before, I don't care about anything after that price is reached. That could be an example. Or it could be a device you are monitoring, and when the device reaches a threshold, you want to respond to it. It could be the fact that you're listening to the weather information, and when the weather changes certain pattern, you want to respond to it. So a lot of these things don't belong to the CRUD model we have been talking about, so we need to really rethink about it. Well, this brings us to 4 different concerns that are extremely important. And one of them is we should rethink about how we develop applications for these kinds of applications. And one of them is to think about message-driven applications. So we want to be thinking about building applications where I'm going to go out and say that using a distributed transaction on a centralized database is so 20th century. We should rethink about how we model applications. Maybe these disparate parts of the system should be exchanging messages with each other rather than trying to use a centralized database or even distributed databases. Well, applications have to really think about elasticity. I got a client, I asked them, how many users do you have on a typical day? And they said, we got about 200 users on a typical day. I kind of laughed and said, really, 200 users? You guys are a multi-billion-dollar company, you got 200 users. And they said, well, you asked us on a typical day how many people we have, and we have 200 people using. But 2.5 days in a month, about 50 million people use their systems. So how do you scale for something like that, where hardly anyone uses your systems most of the time, doing a little admin stuff here and there, and then about 2 to 2.5 days in a month, 50 million people jump on your system. And I'm going to say that trying to maintain a local infrastructure and a staff to maintain it is really ridiculous in this time and age. We should really rethink about how we build systems. And this is what cloud computing has really shown us. We can be extremely elastic. We can be time-based elastic or load-based elastic. When the demand goes up, you're going to make more revenue because of the demand. You can bring in more systems to support your demand. And then when the demand diminishes, you can have these systems go away. Well, the cloud computing and the elastic services have shown this to us. We can definitely leverage that. That's the other thing that reactive programming greatly emphasizes. The third thing it emphasizes is resilience. Resilience is so extremely important. Look at your own smartphones for a minute for me. How many applications do you have on your smartphones? I bet you have about hundreds of applications on it. How many do you typically use on any given day? You probably use a dozen applications. What about the other applications? Well, they're pure crap. In fact, you're so angry at them, you have left them there to die. They don't deserve for you to touch them and even delete it. That's how we feel about applications that are poor performing, not resilient at all. So we should really rethink about how we build applications. Resilience is extremely important because if applications are not very graceful in their failures, we are not going to be very happy dealing with them over time. This reminds me of an experience. I was in a conference not too long ago when a gentleman came to me and he said he was my student a few decades ago. I've been teaching for about nearly close to 30 years now at the University of Houston. And one of the, he said, I took your class on distributed computing back in 1998. I said, oh, I remember that time when I was teaching that course. He said, I want to tell you a story. I said, I love stories. Tell me a story. He said, well, I was in your class in distributed object computing, and we had a final semester demo, and I was doing the demo, and right in the middle of the demo, you walked up quietly to my computer, disconnected the internet cable, and then said, continue, and the project failed, and I failed the course. I said, I'm really sorry to hear that you failed my course. Why would you want to share such a story with me? He said, well, because there's a good news after this, he went on to say, because that's the last day I ever did that mistake. And he went on to say, you see, now when I program, I don't just program the happy path. I start with the things that could go wrong, and I build resilience into the application. And then he said, well, these days when I code, I don't take this so lightly. In my office, he said, in front of me on the cubicle, I have a picture of evil Venkat in front of me. And then I look at this picture every day when I code, and I don't make this mistake. I don't think we want to have a picture of evil Venkat in our desk or in the office. But the point is we got to program for resilience. That's extremely important as well. Well, then, of course, we want to also think about responsiveness. Well, we can think of applications that are working, but we are living in an age of instant gratification. We're not going to just sit around and wait for applications to respond. We want results now, and we want it fast. Well, a good example of this would be to think about infinite scroll, for example. Well, you scroll through this application one morning, which usually is slow. It responded very quickly. And you're like, wow, that was pretty instantaneous. And then you realize at the very end of this particular page, you scroll up and there is nothing. And before you could realize that there's nothing, it filled up the next part of the data. And that's an example of how applications can take the time to work while you are processing part of the response, so it can be very responsive. Responsiveness is extremely important. Imagine you walk into a store and the store is pretty busy, and you see the clerk who is busy with some customer. What do you normally do? You probably look around for a few minutes, look at the ceiling, look at the floor, and you walk away because there was no response. But on the other hand, you walk into the store, the clerk makes eye contact with you, says, I'll be with you shortly, and goes back to help the customer who is already there. You probably waited for a good 15, 20 minutes. Why did you do that? Because you felt you are important even though you know you're not. The point really is that that is the whole idea behind this, is when there is responsiveness, we have loyalty of and the users. And absolutely, the applications that are not responsive are the ones that lose users very quickly. So these are the 4 fundamental things that are essential in building applications. We're going to use message-driven to communicate. We're going to be using elastic services. We're going to program for resilience and be graceful about failure, and of course, provide for responsive applications as well. So what is reactive programming? Well, it is a programming model where we build applications using these things to make the application really resilient and responsive. But how do we go about doing this? Well, can't we just build applications using multi-threading? Well, sure, we can use multiple threads, but imagine what happens when you create threads. That's the easy part. Then we got to worry about race conditions, about how the threads communicate, and so on. That's very, very painful in general. Well, and also, if you really think about it, when you create threads, there is no really good way to communicate between threads. Well, we could use futures for doing this. Well, if you think about futures, though, what do futures do? The futures basically are going to return data to you when the application computation is over, but you could go about and call a future, and the minute the future is in your hands, what do you typically do? You turn around and call get and wait for the response to be given to you. That's no future at all. That's wasting resources while you're waiting for the service. And also, it's really hard to work with it. Oh, wait a minute, can't we all be happy and use callbacks? If you think callbacks are a good idea, I've got a suggestion for you. Just walk quietly next to a JavaScript programmer and utter the word callback and watch them begin to cry unconsolably. Because we have learned that callbacks don't work really well at all. In fact, the JavaScript world has moved on to use promises and other things, and even reactive solutions for that matter. So what is it really that we are trying to tackle? What are we getting to really? Well, the first thing I want to emphasize is maybe it's time to think beyond CRUD. I'm not suggesting that we wouldn't program in CRUD anymore, but not everything we do probably has to be CRUD. The second thing I would ask is, what if we start thinking about data flow computing? What if we start thinking about applications where we have a source of data that would emit data, and we are intermediaries that would receive the data, and as soon as we receive the data, we would perform our computations and in turn emit the data moving forward to the next one in the series, and we can have a series of things that can respond to these applications. Maybe data flow computing is resurging once again. This again is a concept that's been around for a very long time, but it's receiving special attention right now. But to understand this, let's take a slightly different example and play with it. So what I'm going to do is to take a small problem, I'm going to look at a way to solve this problem, and then see how we can go about rethinking about this problem. So for this, I need a volunteer who has a smartphone and who is interested in helping. Who wants to help me? Don't be shy. Who wants to help? Yeah, good. Sir, what's your name? Leo, you can be right there, but I want you to give me information about 3 things. I don't need your smartphone, I just need you with your smartphone. So here's the question for you. Can you tell me the stock price for these 3 things? Google, Amazon, Intel, and Microsoft. I want the stock prices for these 4 things. All right, Leo, we're waiting for you. Do you have the answer for us, Leo? Almost, he says. He's not fast. Anybody thinks he's not fast enough for us?
So Google, $832.
All you have is just one price so far, Leo? This is disappointing. No, he's too slow. Oh, he's asking for somebody's help as well. Well, thank you, Leo. Thank you, Leo. You were wonderful. So you nicely demonstrated how the worldwide weight works. So what did he demonstrate? There are several things. Leo did not know this, but you saw me and Leo together. There are several things that happened here. Thanks for your help. Well, first thing Leo did was we sent a request to him. What did he do? Immediately start on the job, and he's just nose down. At several points, I said, this, I don't care. I don't want you to work on this anymore. He did not notice this at all, just like a web service is. A web service kind of goes nose down working on things. And what happens? When the web service is eventually done, it says, and the result is, like, where did the user go? The user has gone for a long time ago, right? The second thing is, you go to a site, you make a request, the site is taking too long to respond. What do? You want it to help, so what do? You hit the refresh button. That sends 2 threads now working. That's exactly what I did to Leo as well. I kept nagging him more, and now in addition to looking at the answer, he also had to keep responding to me. This is not going to help us at all, but that's the way we've been doing things for a very long time, so you nicely demonstrated. In fact, he kind of branched off to something else along the way, which is pretty smart, but this actually happened in one of the sessions a few months ago. I was doing the same talk, and somebody like Leo volunteered, but right off the bat, he did something instantly what you did towards the end. So when I gave him the 4 stock pieces, that gentleman said, I'm not going to go look up these prices. Immediately, he recruited 4 people around him. He said, you find the price for Microsoft, you find the price for Intel, you find the price for Google. And by doing so, he demonstrated not only can a system suck, you can waste a cluster of machines as well. Well, the point really is that it doesn't really have to be this way. We got to really rethink about the way we do things. So how do we go about rethinking this? And I want to say efficiency is attained not by doing tasks faster, but by avoiding those tasks that shouldn't be done in the first place. So the goal really is to not run faster and faster and faster, but to rethink about how we actually do our work, do our tasks. Maybe there are tasks that we shouldn't do. Does the user really care about this? Can I postpone running this maybe until a later time, and can I maybe do this minimally? Well, I'm going to show you some examples, but before that, I want to kind of connect this. As I was learning about reactive programming, there was a void in front of me, and I didn't understand where does this all fit together. And one of my realizations was this is a really nice segue from functional programming. Because to me, functional programming really is not about immutability. Functional programming is not about higher order functions, while those things are the components, the ingredients that are part of functional programming. For me, the real essence of functional programming really is function composition and lazy evaluations. So if we can attain function composition and lazy evaluation, well, then we can more effectively use the ideas of functional programming. Well, functional programming kind of takes us all the way to the door and says, here you go, we got laziness for you, we got function composition, and reactive programming takes you right from there and says, well, now that you can use function composition and you can be lazy in your evaluation, let's leverage those ideas to move forward. That's where these ideas come from. So where this is taking us is idea of observable. So what is observable? Well, it is the observable pattern, but with certain differences in it. The first is you're going to be pulling the data in the iterators, whereas in observable, the data gets pushed towards you. It could be synchronous or asynchronous. Well, a lot of times, pushing synchrony or asynchrony too early in the game makes the application extremely complex and hard to work with. Well, the beauty in this area is it can postpone. You can't postpone those until a later time. So the observer really has a couple of different interesting things to make this happen for us. Well, the very first thing about observable is that it's got a data channel. And a data channel is through which the data keeps emitting or transmitting towards you. But what do we do when things go wrong? Well, when things go wrong, you want to handle the errors. But the worst thing about errors is we call them exception. Maybe we should have called them normal, because they can happen at any time. So rather than throwing exceptions at you, observables have a separate channel for the errors themselves. So you can this way, there is a data channel and there's an error channel. Well, the data channel has the data, the error channel has the error, and of course, anytime there's an error through the error channel, there will be no more data coming through the data channel, and that's a way for you to know that there's an error. And of course, while you respond to the error, you're not going to be pushed more data towards you, kind of like the circuit breaker model. And of course, I mentioned that it could be synchronous or asynchronous. Let's take a look at how these things can evolve with a quick little example here. So what I want to do here is, I've got symbols as a collection here. So I'm going to say stock server. I'll go ahead and say get feed over here. And I'll pass the symbols given to us to the get feed method. Well, the get feed is going to, of course, give us the data as it's going to happen. But we got to implement it somehow. Well, it turns out there are several implementations available for doing reactive programming on Java. There's not one solution. You could use any of those different solutions. I'm going to just use one of them, which is RxJava, which is implemented by Netflix. Apparently, they had some streaming problems to deal with, so they decided to open source their solution. But the ideas are pretty much the same. The APIs are slightly different here and there, but you could go away and use this in some other library if you wanted to. But the idea of observables really is pretty dominant in this, and I'm going to say observable of stock info is what I really want to use here. So I start with an observable, and that observable, as you can see, is coming from the io.reactivex.observable. So how do I go about creating an observable? How do I use it? We'll come back to that part in just a few minutes. So we'll move on to this side over here. Well, now that I have an observable on my hand, I'm going to say that's the feed. And then, of course, I'll go ahead and say got observable, and I have an observable at my hand. But I want to go ahead and do something with the observable. I've not done that yet. We'll come back to that in just a minute. Going back over here, I'm going to say observable.create. And this uses the idea that we don't want to use a constructor, but we will use a factory method to create an object. So we are saying observable.create to create the object. So in this case, I'm going to get a subscriber to be given to me. And I'm going to go ahead and emit into this subscriber some data as it so happens. So we need an emit method for us to be able to use this now. So the observable is created. The observable gives you a reference, and observable is nothing but a data stream. Oh, wait a minute. Let's quickly talk about what is the difference between observable and stream, as we know streams in Java 8. Well, there are a couple of very clear differences between them. Well, they both, streams in Java 8 and observable, are data emitters. So they both are going to emit data towards you. But the stream API in Java 8 do not deal with exceptions at all. On the other hand, observables have a clearly separate data channel and error channel for one, so they have a better handle on dealing with exceptions or errors for you. And the second thing, of course, is that they both are lazy, of course, so they could be sending data at any time. They will be pushing data towards you, but the way they handle data is one of those differences, if you will, in how they handle with things. So in this case, I'm going to create an emit method, and in the emit method, I'm going to go ahead and say this is going to be receiving a subscriber, and it's going to emit the data. So I'm going to say start emitting over here, so we can actually see that particular method call as well. But right off the bat, let's go ahead and run this and see what it's going to do. And you can see that it said got observable, but it didn't do anything more, just to emphasize the fact that it is absolutely lazy. So it's not going to do any work until you really demand a connection to it and say, I am really ready to process your data. It doesn't really start emitting any data. It's that lazy. Well, now that we are receiving here, why don't we go ahead and do something with the data? So I'm going to go to the feed and say subscribe, and now I can say output. So in this case, I'll simply say system.out.println, and I'll just print the data in this case so that we can see the data being transmitted towards us. Well, of course, in this case, I'm not still emitting any data. So when I go ahead and run this code, though, you can see it said got observable. It said start emitting data. But the start emitting data really happened because we truly subscribed to the data. Well, now what I'm going to do here is to go back to this emitter. And I'm going to say at this point, why don't we say while true in this case. And then I'm going to say, well, we got the subscriber on our hand, but I also like to have the symbol given to me as well, because that would be, after all, pretty useful to have. So in this case, I'm going to pass the symbol to this as, let's say, the second parameter. So now I can say in here, well, now that I have the symbols at my hand, I'll say symbols dot, and then I will go ahead and say stream. I'll use the Java 8 stream. This is purely an implementation detail at this point. Then I'm going to say map, and I'll say stock info, and I'll call a fetch method. Well, the fetch method of stock info is going to go out and get the stock price, parse the data and give it back to us as stock info. And then once I have the data, I'm going to say for each. And in this case, if you give me a stock info, I'm going to say subscriber.onNext and send the stock info to that particular, oops, wrong one. And in that case, I'll say stock info, and then I'm going to say stock info, and I'll just go ahead and send the stock info to this object at this particular point. Well, in this case, of course, the map is going to return a stock info. We could receive the stock info and pass it on to the subscriber at this point, or we could just simply use the Java 8 syntax and say, well, we could simply use a double colon on this. But the whole point is, irrespective of the syntax, you can think of this as the mouth of the data channel, where you start emitting the data through the data channel of the observable. And of course, now that you're emitting the data from here, the data should be arriving on this other side. ArgsJava itself does things within one particular JVM. But if you really want to go across the JVMs, there are other solutions. Again, one example of this is Vertex. Vertex actually uses RxJava API, but wraps and gives you the ability to go across machines as well. So you could use one of these different solutions to deal with. So as you can see, this is getting the data, and Google is pretty close to what Leo pointed us to us. So thanks, Leo, again. But you can see that the data is arriving at this point, but this is just transmitting the data for us, and we are receiving the data. So, but where does this lead us to? Well, this is a synchronous solution. We are transmitting data. But where we really want to go from here is an ability to interact with the systems and communicate across these different endpoints. So in here, imagine you have an observable sending data towards you, but there are times when we should be very mindful of resources. The observable, the source, is using resources to talk to you, and you are using resources to receive the data as well. And what if there is no more data coming towards you? It would be nice to be told that there is no more data coming towards you. Well, this is where I said there are two channels. Well, I kind of lied to you. There are three channels. There's the data channel through which there will be data coming through. There's the error channel through which an error may come through. And there's a complete channel through which a signal for complete comes through. Well, the way the observables work typically is there might be a 0 or more data coming through the data channel. So imagine there's a data coming through the data channel, and at any time it's going to tell you there is no more data. Well, it's going to send a complete signal, and the minute it sends a complete signal, the data channel closes up, and there will be no more data coming through the data channel. Well, just to illustrate this point, let me go back here to this code and say, in this case, let's say count is less than, let's say, 3. And I'll go ahead and start a count is equal to 0. And in this case, let's go ahead and increment this count for our purpose. And then in the very end, I'm going to say, go ahead and say subscriber.onNext, and then send a new stock info. Let's go ahead and say info of dummy, and then 0.0 as a price, just to illustrate the point about the way these channels actually work. So when I run this code, you can see the data is being emitted at this point, and the data is going to be pulled from the service. Oh, looks like my internet connection is a bit slow here, so it's not respond. Oh, there you go. So it starts moving. Okay, it's terribly slow. All right. So now you can see eventually it's a dummy 0.0. But on the other hand, I'm going to go back here, and at the very end of this, I'm going to go ahead and say subscriber.onComplete, and I'm going to send a complete signal. Well, on the receiving end, I'm going to go ahead and add one more thing. For now, I'll just say system.out.println. We'll worry about what this is in a few minutes. But I'm going to say I'm receiving no data, but I'm going to simply output done over here as the very last one. Well, if you look at these things, these three lines are really the three different things that we are talking about. The first line is your data channel, the second line is your error channel, and the third line is your complete channel. So there's a way for you to receive data, one of these three channels for you, so you can either be receiving data through the data channel, error through the error channel, or the complete signal through the complete channel. But in a sense, though, notice that I put a dummy out in the very end after complete. But remember that once the complete signal comes, the data channel closes up. So that's why in this output you notice it says done, but it never received the dummy out as the output. That's because the minute complete signal was sent, the data channel closes up, and this becomes purely a no-op. It's never going to leave the observable and go to the client. And of course, the observer or the client or the subscriber can do a cleanup operation right there. This gives you an idea how you can send a signal from the subscriber to the observable to the observer and say that I'm done. But what about the other way around? There are times when you want to unsubscribe as well. So for example, if I go ahead and say, give me all the stock symbols and the prices, and the observable start transmitting the data to me, but at some point I realize the price of the stock is my favorable price, I want to perform a trade, I no longer want to get the data from the server. Well, I could send an unsubscribe and say, thanks, but no thanks. Don't send me any more data. So this gives an opportunity for you to unsubscribe from the source and say, don't bother sending this to me anymore. So in this case, what you can do is you can throw in an unsubscribe as well. Well, we got to do a little bit more work for that. So what we could do in this case is we could go ahead and build up a new, and we could say we'll call this as my observable. So I could create my own observable right here, observer rather. So I can create my own observer. And in this, of course, I have my observer. And this observer can, of course, implement a certain methods that are required for starting to observe. So we could implement a bunch of methods on this observer. Well, this observer, of course, is going to support the interface that this subscriber is expecting, which is the observer. So we could go ahead and create a little class here. So we could say, for example, new observable, well, observer rather. And then we could say, I want to implement the methods that this guy is going to expect. So let's redo this right here. So we can say feed.subscribe, and new, we'll call it as observer. And then this is going to be the stock info of the observer that we would like to go ahead and implement it. Well, in this case, of course, we're going to implement these methods. So what are the methods I'm going to implement for this purpose? Well, I'm going to implement the method which is the onNext. We saw that earlier. So this is going to be simply the stock info that I want to respond with. So this is going to be, pardon me, I made a mistake here. This should be info rather. So that's a stock info that's the observer going to get back to us. So we can simply say, I'm going to receive the stock info. And this case, of course, I'm going to say, print out the stock info. So I'll just print the stock info given to me. I can also print the complete signal right here, ignore the error for now. And then, of course, I can say done right now. But I can also do one more thing. For example, let's say on the next, I could say if the stock info dot value is, let's say, less than, let's say about $40, we could immediately say output, unsubscribing. So we could say unsubscribing, and we could then send a request to unsubscribe. Well, how in the world can we do this? Well, we could say in this case, we are receiving a disposable. So I will go ahead and store that away here as disposable, and we will store that into a variable. So disposable equals the given disposable. And then we can nicely go back here and say the disposable dot, and then we could dispose off and say, don't bother sending me any more data. So we can see the transmission of the data starts up depending on how the internet is going to send the data. Well, as the data arrives, the minute the data is less than a 40, we can unsubscribe right away, and we're not going to get any more data moving forward. That is an example of how we can go ahead and unsubscribe from the calls at any given time. So the observers can say, don't bother sending any more data to me, and that way they can be very mindful of resources the server is going to use as well. Well, that gives us an idea about how we can process it. But the big elephant in the room, of course, is how do you handle the errors? Well, errors are something extremely important to deal with properly. So in other words, what happens when things do go wrong? Well, when things go wrong, imagine you're in a multi-threaded application. And in a multi-threaded application, when things do go wrong, you want to be able to know, what went wrong, and you want to be able to handle that. Well, when you have 1,000 threads, and if several threads begin to fail, there's no real good way to communicate all that information in a multi-threaded situation. It becomes really hard to work with it. What we're going to do here instead is, exception handling is something we have really struggled with throughout almost the history of computing. Well, what did we do a long time ago? We said, we're going to return a result. If the result is positive, it's a good data. If the result is negative, it's an error. Then we realized, gosh, that doesn't make sense because the data could be negative too. And then we tried something else. This was the days of the 80s. We returned an error all the time. If it is 0, it's good. If it's not 0, it's an error. Yay, that's awesome. But wait a minute, where's the data? Oh, you will send an extra parameter to the function. The function will fill the parameter with the data and return to you. That made things very clumsy for us to use. And one of the errors you had to deal with was that the function forgot to fill the data in the first place. Or you forgot to send the proper holder for it. Okay, that didn't go really well. Then what did we do? We said, we're going to do exception handling. Exception handling was wonderful, wasn't it? Because a function could throw exception and you could simply ignore it with an empty catch block. That was frustrating. I can tell you, a week doesn't go by when I plead with the programmer, please no empty catch blocks. That didn't go very well at all. And there's another thing. When something goes wrong, what happens? It throws an exception at you. How civil is that? How would you feel when people throw things at you? Well, reactive programming is extremely civil. It doesn't throw anything at you. It hands you the error and says, here you go, and shakes your hand and says, we'll be civil about this. That's one of the really nice things about it. It takes the exceptions, but it gives you the exceptions through the error channel very nicely. Let's see how that works actually in this example. So I'm going to go ahead and say system.out, and let's say println. Well, we know that this is going to be the data channel coming through. But I'm going to say, given an error, I'll go ahead and output error right here in uppercase. And then I will say plus over here. And then I will just print the error. And then finally, here comes the data. We'll say output done to say that we're going to receive the output as the complete signal. Well, when I run this code, in this case, of course, you can see that things are going well. And you are getting the data, and eventually you're done. But on the other hand, let's say in this case, I'm going to go ahead and increase this to, let's say 300 for a minute. But I'm going to go to my stock info. And in the stock info, at a random time, I'm going to blow up with the, oh, oops, ran into trouble. But notice, this is going to throw an exception. But this guy is not dealing with exceptions. However, the reactive system says, oh, wait a minute, you are transmitting, emitting data. And while you're in the source of the data emission, something went wrong and things blew up. We're not going to just simply throw. We're going to capture that exception and send it as an error. In other words, errors are first-class citizens as well. You're not treating errors as something secondary. You are treating them with as much respect they deserve as the data deserves, and that is one of the nice things about it. So when I run this program this time, though, notice it starts emitting the data, but notice when things did go wrong, when it blew up randomly, that exception was grabbed, and notice the word error in front of the message. That error came right from there. Whereas the exception I threw really had, oops, ran into trouble. And that shows how that exception over there was grabbed, but politely given to you through the error channel in a way that you can actually handle. Furthermore, when the error does come up, the data channel closes up. There will be no more data coming through the data channel, and you can handle and deal with the error properly on your side. So that shows how we can handle errors as well very nicely. Well, I want to just touch on just a few remaining things in the time we have that we need to really think about as other considerations. I showed you a fairly simple example here of an observable and an observer, where the observable emits data and the observer is using the data being transmitted. But there are typically a lot of different things we would normally want to do. Let's go ahead and remove this error for now, and then we'll continue further. Now, in this case, of course, if I run the program, that's going to start transmitting data for quite a while, as you can see in here. But there are things you can actually do quite effectively along the way. For example, notice the prices are ranging from $800 on one side to, all the way down to $35 and so on. But let's say that I'm actually interested in only certain values that I'm interested in observing. Well, what I can do in that case is I can nicely use this approach to build up on these things very nicely. So for example, if you go back to this code, I'm going to remove these messages for just a minute so we can just see the data coming through. You can see that in this case, once I turn it on, we're going to have the data coming through and it displays all these data. I'll stop this for now. But what I can do is I can say, Well, I don't want to see all the data. Imagine for a minute that you are dealing with a situation where you are looking at a device, the device is transmitting data, and you are not interested in all the data. Well, let's say for a minute, I'm an observable, and I'm emitting data constantly. And let's say Leo here is an observer. He is interested in receiving some data I'm sending. But a little bit later he says, you know what, hey, this is great, but I don't want everything that you are emitting. I only want certain things that you are sending and not other things. Well, unfortunately, I don't want to deal with Leo's request. Well, not that I don't care about him, but we'll use a technical term for it. It's called cohesion and single responsibility principle, right? Well, I'm going to do what I'm going to do. I don't want to start customizing what I do for just one of my observers, but because somebody else may really care about everything I send. So what do? Well, we're going to have an intermediary right now. This intermediary says, don't worry about it. I'm going to sit between Leo and this observable, Venkat, and it says, I'm going to start filtering out things that Leo doesn't care about. This is a very powerful model, as you can see. Notice we have the feed up there, but the feed actually is right this one returned by the getFeed method. But right here, I'm going to say dot filter, and I'll say stock info over here. And then I'll say, in this case, stock info dot value that I'm going to get from it is, let's say, greater than 40. So we can immediately say, well, when the observable is going to start emitting data towards me, I can take the data the observable is emitting, and I can start filtering the data that gets emitted right here. Let's see why I was not too happy about it. So I can start filtering, and I can say stock info, and then I can say stock info dot value is greater than, let's say, $50. And then you can say, I'm going to start emitting data, but only if the data is, I'm going to send data only if the data is greater than that value, not otherwise. Now the beauty is, you can take this feed, but you can put multiple intermediaries that are observables to what's upstream, but they themselves become observables to what is downstream. So on one hand, they are observing. On the other hand, they can become observables downstream as well, and they can start filtering things. As you can see, no price now is less than $50 at this point. Likewise, you can do other things as well. You may say, okay, Venkat, but it would be really nice if you can give us a little discount on the price. So we can say stock info. Now we can say stock info. We could provide the stock info.ticker, but we could take the price given to us, the value rather, and then we could say 0.9, and you start getting a 10% discount on the price. So you can see the prices no longer are $800, much less than that. So we can have these kinds of intermediaries working really well. But not only can we do this, we can also get to a situation where we can nicely say that I want to receive data, but I don't want to be bothered by a lot of data. So you could say something along the lines of, you could say dot take, and I'm going to say, let's say 5. So this says, I only like to take 5 pieces of data, and don't bother with me any more data. What's the difference between filter and take? Well, filter is kind of like a little flap. It will block a data and say it can't go through, or would let some data go through. So per data, it might block or release. Think of a take as like a valve. So it is open to begin with, the data keeps going, but when the condition is reached, the valve closes up and no more data will go through. In fact, it's a little bit more than that. The take is an observable that will start transmitting data. In other words, it will duck. So whatever data is being transmitted will go past it, but when the condition is met, it is going to send an unsubscribe upstream, and it will send a complete downstream. So notice in this case, when I run this, once the value 5 is reached, the take is going to take the responsibility of transmitting a complete signal. Notice the done came actually from the take sending a complete signal, and that is already baked in. Well, the take, of course, is going to give us only an ability to take on 5 data, but it could be pretty logical as well. You could do a take while, and you can say that while this condition is true, keep sending data. When that condition is not true anymore, stop. So in this case, you can say, keep sending me data until a certain stock price is this value, but the minute it reaches a threshold, quit sending me data. I don't want to hear this anymore. You can be very logical about it. Likewise, you could not only a take while, you could also do a skip and a skip while as well, and then you can be the opposite of what a take is doing. So, but then of course, this works great, but when you have multiple observers, how do things actually work? Well, this is where a difference between what are called hot observables and cold observables come in. A cold observable is the default. A cold observable will maintain multiple sessions concurrently. So in other words, if Leo subscribes to my observable, I'm going to be transmitting to Leo. At the same time, when Sarah subscribes, that's a completely separate session. So in other words, it's like me messaging. I'll be on a message session with my wife. A friend of mine may join. I'm going to have two distinctive sessions. I'll say stuff to my wife and I'll say different stuff to my friend. They both are in completely two different messaging sessions. I am a cold observable. On the other hand, it is possible that my wife is chatting with me when one of my sons come along, and I might decide the topic is of common interest. I might put them together on a message. Now I become what's called a hot observable, because both my children and my wife can participate in the same conversation with me. I maintain one session, not multiple sessions. So we can have these kinds of distinctions between if all the observers are viewing the same thing from the observable, or are they having distinctive sessions. We can manage that also very effectively, as the case may be. But not only that, we say, okay, this is all great, but what if the observer is transmitting data at a certain pace and the subscriber, the observer, is not able to keep up with it? What are we going to do? Well, this is where what is called back pressure comes in. So a back pressure is where you can configure how the system is going to respond when the rate of transmission changes suddenly. So there are a couple of different options. One back pressure is back pressure drop, meaning I don't care, I'll be processing at my pace. If the data is too fast, just get rid of the data. When I'm ready, I'll get the next data. There are some situations where that is the right thing to do. There are other times when you want to buffer the data. So there's an on back pressure buffer, which will put the data into a buffer, and you can be pulling the data out and processing it at your pace while the data keeps streaming in and gets buffered. Again, of course, that only makes sense if there are peak periods and non-peak periods where you can recover and start processing data. So these are different approaches. You can also do what's called throttling, where you can start throttling and saying, I don't want to be getting this data at this pace. I want to vary the pace at which I get the data. There could be a lot of noise from this, and then when the data settles down, I want to receive it. One example of throttling is where you are, let's say, observing somebody typing on the keyboard. My wife says, I'm extremely good in typing backspaces. Well, that's kind of annoying, right? Because we type and then we delete, type and delete, type and delete. And you could say, why don't I let the user type and stabilize what they really type? Then I will take what they type and process that. That's when you could be using things like throttling, where you give them opportunity for the noise to settle down, and then you can process the data. All of those approaches come in really, really handy. So to summarize what we talked about, the idea behind reactive programming is to be able to really create a system which is elastic message-driven, very responsive, and also very resilient. And there are so many different solutions. Hopefully this gives you an idea about what reactive programming is all about. If you're interested in downloading the code examples I showed you here, they are located at that URL on my downloads page. I hope you found that useful.